1. Okay, here we go. We are getting close to the end. I am in a very squeaky chair, so I'll try not to move around too much. So I'm actually recording this in my office for once, not in my basement. Exciting. All right, so what's the plan for this week here? Well, it's all about our good friend integration. So we have rigorously studied differentiation, and so naturally, again, our goal in this course is to do calculus right, and after differentiation, it's time to discuss integration. Right. All right, now first off, I do want to point out, this might look, hello. This 37 might look a little daunting, but as you will see, the rigorous definition of integration is not too difficult. It is a little sprawly. So even though it says 37 slides, a lot of the slides are just sort of, you'll see. All right, anyway, so as per usual, let's start off by recalling how this information was presented to us in calculus, and then we'll talk about how to make it rigorous. Okay, so, all right, so in our Calc 1 course, integration, which again is represented using the symbol, was built as follows. You create Riemann sums, and what that means is you take your interval AB, you break it up into a partition, where x naught is a and xn is b, and the partition is strictly increasing, so x1 is bigger than x0, x2 is bigger than x1, so on and so forth. The c sub x's are chosen to be anything in these sub-intervals. Now, of course, the three main ones that you probably talked about were the left-hand rule, the right-hand rule, and, of course, the midpoint rule. Either one of those three, it doesn't matter, you just pick whatever point it turns out. Here, the distance between the points. Now, usually when you set up a partition, you have it be uniform, and we'll talk about that a little later. And then this symbol here to denote what was called the mesh of a partition, which is the largest length of a subinterval. Right, and so the Riemann interval is defined to be the limit of all such Riemann sums as we let the mesh, the size of the subintervals, get arbitrarily small. So basically you've got your curve, and what we're doing is stuffing rectangles underneath them, base times height, and we're letting the width of the rectangles get arbitrarily small and take the limit of that. All right, so there you go. Now, immediately, you hopefully notice there's probably a bit of a problem, because what exactly does this limit mean? Right, because when we discuss limits, we always had x going to 0. Here I'm talking about like norm, right? Is this symbol legitimate, right? It doesn't immediately fall into the paradigm that we set up, so that limit needs to be addressed. However, all of this stuff should be reasonably fine. So, as usual, our goal is to make this rigorous. In particular, it's supposed to be a limit. Note I put limit in quotes here. So there should be some sort of way of describing this using epsilons and deltas. And that's what we'll do. And what I'd like you to do right now, this is a pause the video moment, look at this and think of what an epsilon delta definition for this would look like. Right? How would you rewrite this in terms of epsilons and deltas? Okay, so take a minute, think about that, write it down, and then at the end of the video, when we actually get to it, see how it matches up. See if you've got some good intuition building. Okay, and it's not too bad, right? Because obviously an epsilon is sort of, well, I need these things to get with an epsilon of something. The trickier part, as we're going to see, is how do you get the delta thing out of this? And we'll see. All right, let's begin the process now of making this rigorous. So the first thing is, let's formally describe what a partition is. So in an interval that's non-degenerate, so a closed interval from A to B, non-degenerate, a partition is a finite subset that has the endpoints. That's it. Any finite subset that has both endpoints is a partition. Now, note, because it's finite, that means we can put it in a list. The list has at least two things in it, because it has A and B, so that means I can list it using a natural number, which starts at 1, x naught, right, 0, not in the set, so this thing always has two elements, and in particular I can list them in increasing order, so x naught will always be chosen to be A, and xm will always be B, and then the other ones we will just always assume they are listed strictly increasing. For any finite set, you can do this. It's finite, so you can list it, and then pick your favorite sorting algorithm and sort it. All right. Right, so given a partition P, it has a listing of elements, and again, note this listing is actually unique. There's only one way to do that. Then we can define the deltas of x1 to xn by just taking the difference of the bigger one versus the smaller one. So note the delta x of k is always strictly positive. Right. So thus, right, these are just all the lengths of the subintervals that we can form. Okay, and note that there are n of them because I have n plus 1 points. Right, you have n plus 1 points, and if you cut a thing into n plus 1 pieces, there are n sub-pieces. All right. Now, again, note this is strictly positive. The other thing that we need to note about this that we're going to use is that the summation of all of these things would just be the sum of all of these, and note that's telescoping. So we just pick up the last term minus the first term, which is b minus a. And we are going to be a little tricky when we use this, so keep that. Put that in the back of your brain, we will be using it. Okay, so that's the first part of creating Riemann sums. What is a partition of an interval? And again, just a finite subset that has the endpoints. That's it. All right, now let's talk about how you actually get the Riemann sum part of it. So the traditional way of doing Riemann sums is, then you just pick any element in your intervals and you look at the rectangles that you can form there. All right, now you can do that. However, it turns out that if you want to start trying to prove things with that, you're going to have a very bad time. While the intuition of Riemann sums works very well, in terms of forming appropriate epsilon deltas, it turns out it's going to be a lot easier to go with a different approach. And this is the approach that's known as the Darboux approach, named after a mathematician whose last name was Darboux. And Darboux's approach was to remember that we're dealing with the real line. And because we're dealing with the real line, if I have a set that is, bounded above, I have a supremum. If I have a set that is bounded below, I have an infimum. So Darboux looked at what Riemann did and went, well, you can make this a lot easier if you introduce sups and infs. And so that was his approach to integration, which, as we were going to prove, will give us the Riemann sum interpretation. Okay. So, given any partition and any function that has a lower bound of alpha and an upper bound of beta, we always have access to this infimum and this supremum for each subinterval, and the horribly bulky notation that I'm going to use is this. Your textbook just calls m sub k and capital M sub k, but it obscures the partition and the function, so I don't like that. And as we are going to see, we are going to have to do some proofs with these things, and we're going to have a nice enough notation to work with, so this is the notation I'm going with. It sucks, I agree. And that, as I already said, is kind of the hard part of working with the Riemann integral initially, is that the buildup is just a lot of gross notation, and it just takes up a lot of space. But anyway, all right. Okay, so one thing to note, and it's one thing that we're going to... This chair sucks. One thing that we're going to use a lot is the following fact, that if you have a partition and a function bounded below by alpha and bounded above by beta, then the infimum of the function on the subintervals, of course, is always less than or equal to the supremum of the function on the subintervals. But it's also, this will always be less than whatever the absolute upper bound of the function is, and this the absolute lower bound. Now note something, if my function was, nice and continuous, these are actually mins and maxes. These are not supremum and infimums by the extreme value theorem. I wonder if we're going to use that. Ooh, I don't know. All right, so we've now defined partition, and we've now addressed, so we've got the delta xk, and now we've addressed the f of ck, where what we're going to do is go pump the brakes on that. It turns out using these infs and sups is going to be a lot better, because, again, infs and sups are what make the real numbers, so there's going to be some things we can pull. So, all right. So then the upper and lower Darboux sums are defined to be the following. So note they look very similar to Riemann sums, only in a Riemann sum, this is actually a output of the function, and so is this. However, our assumption is just that our function is bounded, so it has the infs and it has the sups, but it may not actually obtain them. All right, so it's not a traditional Riemann sum, but it's a thing that looks like if it uses the analysis machinery that we've built up, supremums and infimums. These are called lower and upper Darboux sums. Okay. Again, like I said, because this was developed not by Riemann, but instead by somebody named Darboux, whose name has already popped up. As we noted, Darboux proved that a derivative will always have the intermediate value property, which then gives us examples of functions that are not continuous but obtain all of their intermediate values. Okay, so all right, we've set up enough to prove our first our first proposition. Okay, and let's read it out. What does it say? Let's say we've got a non-degenerate interval AB. We have a function defined on it, and our function is bounded below by alpha and bounded above by beta. Then for any partition, alpha times beta minus a, so the lower bound of alpha times b minus a. Now imagine what this looks like. Base times height, because again, remember, we're stuffing rectangles under a curve. So base times height, base times height. So this rectangle is always bounded above by this bigger one over here, and that the height is potentially bigger, and in between them are any one of these upper and lower Darboux sums. And again, these upper and lower Darboux sums are just the Riemann sums. They're rectangles being stuffed under. The only difference is that I don't necessarily know that this is an actual output of my function. Okay. So what it's doing is kind of being a little bit more efficient, where in the Riemann sum you just arbitrarily pick something. In the Darboux sums, we're kind of being really efficient in our choice. We're choosing the smallest possible thing we could and the biggest possible thing we could. And so we're going to add those up and compare them. And obviously the lower one is less than or equal to the upper one. All right, but let's actually work out the details of this proof, even though you might be able to visually see why this would be true. The proof of this is going to give us a bit of a flavor, a little amuse-bouche of how the rest of the theorems are going to go here. So it's a partition, which means we can write it as x naught to xn. All right, for each k, our hypothesis ensures that alpha is less than the infimum of the function on the k subinterval of the partition P, right? And the maximum, the supremum of the function on the k subinterval of the partition P is less than beta, all right? And as we already noted, the sum of all of the deltas, the length of the subintervals, must be the length of the whole interval, b minus a. So if we look at alpha times b minus a, well, b minus a we proved is equal to this. Alpha is always less than or equal to that. The delta xk's are always positive, so this is always less than or equal to that. This is always less than or equal to that, and these are positive. And these are always less than or equal to that. So then we get there, and there we go. Proof over. Yeah, not too bad. Right. It's not awful at all. It's just there's a lot of notation flying around, and that's, I said, going to be the hard part. That's really going to be the challenging thing here, is just keeping track of these notations, right? And again, like I said, your book does not go this hard with the notation. They just go capital M sub k and lower m sub k. And I don't like that because it kind of hides some of the more important things. And right, you're never just dealing with one m sub k. You have multiple ones with different partitions and different functions running around. So I think this notation help with the technical proofs that are going to come, but the buy-in's a little bit more. So, all right. So speaking of technical proofs, here it is. Okay. So I am not overstating things here when I say that this is probably the most important thing we're going to prove about Darboux sums, and thus about Riemann integration. This turns out to be the key move. This is the linchpin. This is the thing that basically lets us get away with all the theorems. And I'm really not joking. You'll see it in action. Okay. All right, so let's read what it says, and let's get into the proof. Okay, so again, we set up what we got going on here, a non-degenerate closed bounded interval from AB. All right, and I've got a bounded function, and I've got now two partitions where one of the partitions contains the other one. Okay, so I didn't want to avalanche you with verbiage here. R is sometimes called a refinement of P. And if you think about what this subset is saying, is that we've got P, and now we've just added more points, so we've refined the partition. Okay. And right, and if you think about that in terms of the Riemann sums, then what we should be getting are more accurate Riemann summations. right? And so that should mean that the lower ones only get bigger, and the upper ones only get smaller. Right, and again, that hopefully makes sense. If I start adding more points, right, my lower could only get bigger. If I start adding more points, my upper can only get smaller. Right, and again, remember this is built off of infimums and this is built off of supremums, and that checks and that right, that tracks with how we have experienced adding points to sets, looking at subsets and infimum and supremums. Okay, so hey, there's two inequalities, so guess what we're doing? Only one. And it's even worse this time, because all I'm actually going to prove is the first one, and I'm going to only prove the case where r is just p with an extra point. Obviously, if r is equal to p, there's nothing to show. Now note, r must be finite, so if I know how it works for one, then you can just induct your way up to the others. So some details of the proof are being left out here, and yeah, I don't care. You can fill them in if you really want to. All right, because as you're going to see, this is not a fun proof. This is a just index management proof, so it's not. It's a very dry. This one was left in the oven a little bit too long, unfortunately, and it's just, you know, sometimes you just got to do it. All right, so let's get through it, and once we've got it, we can start using it, and then we're gonna get to the juicy theorems. So, okay. First things first, P is a partition, so I can list out its n elements, whatever they may be. All right, now note Y is not an element of P, but Y is in R, which means it's in AB, so it's strictly bigger than X naught, but it's strictly smaller than Xn, and so somewhere in between it's gonna live, right? So there is some J where Y is strictly hanging out between X sub J and X sub J minus 1, and note that J would have to be unique if we cared about that. We don't, we just need to know it exists. All right, and there we go. All right, so equipped with this knowledge, then, we can create a partition for R, a indexing for R. Now note, R only has one more element than P, so an indexing for it should go up to n plus 1. And formally, it's as follows. Up until j minus 1, the indexing for R is the same as the indexing for P. It is until we get to J, where then all of a sudden Y shows up. Now, then, that's what we define Y sub J to be. And then for Y sub J plus 1 and beyond, well, then we just throw in the elements from the partition for the indexing, for P. And there you go. All right. So, right, that makes a lot of sense, right? You've got a listing of elements for P. I have an element that lands in between J minus 1 and J. All right, well, now just call it the Jth element and then shift all of these over by 1. And that's it. And that's all this looks like. All right, beautiful. Okay, so note, Y sub J plus 1, plug that in, is X sub J. All right. Okay, so now we see that we've got this, and so now we want to figure out why this partition can only get bigger. Well, before we go into that, note that up until j minus 1, all of the terms are the same, so the lower Darboux sum of the partition P is the same as the lower Darboux sum on the partition R, up until that point. Then we get here and things are going to change, and then note, from there and beyond, they're the same, so nothing changes. So the less than or equal to then is going to come out of this. So let's start actually writing out what I just said. So for k running between 1 and j minus 1, the subintervals for p are the same as the subintervals for r. The lengths of those subintervals are the same. The infimums of the function then must be the same. So we have equality. So for 1 to j minus 1, when I add up my infimums times the length of the subintervals, I make my lower Darboux sum, nothing changes. They are identical. That's it. All right, so the interesting thing, of course, is what happens when we hit k equals j, right? That's where y shows up. Okay, and that's where the less than or equal to is going to come into play. All right, so specifically, if we look at y sub j minus 1 and y sub j, note y sub j minus 1 is still x sub j minus 1, but y sub j is y, and y is less than x sub j. So that means this subinterval is contained in this one. which means the infimum of our function on the larger subinterval can only be made larger by going to the smaller subinterval. If I start taking stuff away, I can only get bigger. I can't get smaller, right? Because, right, yeah, other way around. Right. Once if I start taking stuff away, right? Yeah. Anyway, yeah. If I start adding stuff, that's what I want to say. Right. So, right, the infimum here, right, can only get smaller because you've added stuff. The other way around. Anyway, there we go. All right, beautiful. Okay, so here we see that the jth subinterval of P, the infimum there, cannot exceed the infimum on the jth subinterval of R. So we have this inequality. And similarly, the jth subinterval infimum of the partition P will not exceed the jth plus 1 infimum. Now note, the lower Darboux sum for the partition R has an extra term, and so now we see, the jth term in the lower Darboux sum of P is less than or equal to 2 terms out of the lower Darboux sum of R. All right, so far we've only accounted for j minus 1 on both, but now we've accounted for j for P and j plus 1 for R. Okay. And note here, all I'm doing is our favorite trick of sneaking in a plus and minus 1. All right, beautiful. All right, and so there we go. The proof now is effectively over because we've now justified why an inequality shows up, because when we look at the rest of the subintervals, they are identical, so the Darboux sums line up. It's only at that jth spot where the inequality jumps in, because on that jth subinterval, we split it in half, essentially, or we split it in twain, and then the lower sums could potentially get bigger. All right, and there we go. We have proven it. Good. So, like I said, not bad, right? It's not awful. It's just a lot of notation flying around, which makes it visually a bit stomach, I guess. But overall, it's not too hard of a proof. Okay, beautiful. Right, like I said, the notational overkill that I'm going with, right? Your book uses lower, just m sub k, and then if he has extra, and then if Leibel has extra m's, he does m star or something, and it's not descriptive to me. It does make my notation maybe a little bit uglier, but whatever. I'll take ugly notation that's very clear versus clean notation that hides stuff. All right, but anyway, so like I said, this is kind of the main thing because, as we will now see, it's going to tell us something very important, and it will give us the key step in defining the Riemann integral. All right, so in a bounded, yeah, I need to get out of this chair. I'll do that for the next videos, or just not move. Impossible. You don't see it, but I'm like, whatever, my arms are flailing around everywhere. Okay. Anyway, all right, so we proved a technical result. All right, and the math gods only let us do that if they want us to use them. So let's use it. All right, but in order to use it, we got to set up some stuff. All right, so given a non-degenerate interval and a bounded, I changed it, but then I didn't build it, any bounded function. The set of lower Darboux sums, note, is bounded above, right? In particular, it's bounded above by the largest possible rectangle, the beta times a minus b minus a that we discussed from before. And likewise, the collection of lower Darboux sums is always bounded below. So this collection is non-empty, right? There are always partitions, and it's bounded above. And this one's bounded below, so note, a collection of lower sums bounded above, a bunch of infimums bounded above, a bunch of supremums bounded below. So we're going to have a soup of some imps and an imp of some soups. Oh, we've seen that before. All right, so this thing here is called the lower Darboux integral, and this here is called the upper Darboux integral. Okay, so not quite the Riemann integral just yet, but note something about these. For any bounded function, you can always create these. So very similar to, I don't know, limits, where for a bounded sequence, we always have access to the lim inf and the lim soup, but the limits may not exist. But it does probably when these are equal to each other. Yeah, maybe. All right, so there we go. That is the lower and upper Darboux integrals, which we represent by putting a little bar on the bottom or the top of the integral. This is pretty standard. I don't think I've ever seen any other notation for describing upper and lower Darboux integrals. This is not a standard, speaking of standard, this is not standard in LaTeX. I have code if you're interested in how I create it, but by I have code, I mean I googled how do I make Darboux integral in LaTeX, and then I went to the Stack Exchange thread that explained how to do it, and I just copied and pasted it. But if you don't want to do that search, just want to email, I can send it to you. All right, cool. All right, anyway, so we always have access to these, and again, I'm deliberately pointing out the analogy to a bounded sequence. This being essentially the lim inf, and this essentially being the lim sup, and the lim inf is always less than the lim sup. Potentially strict, but this here. Now, for us, though, right, this isn't exactly a lim inf, and it isn't exactly a lim sup. It's something different, but the intuition is the same. All right, so what we got to prove before we do anything is that the lower Darboux sum and the upper Darboux sum, the inequality that you want to be true, is true. Right, it would be awful if this was not true. If the lower one could get bigger than the upper one, that is a terrible name for it then. Alright, but indeed these are always less or equal to each other, so let's do the proof here, and that's why the previous proposition was done. Okay, so take any partition for AB, then if you take any other partition, the union of those two must be a partition, right? It's a union of two finite sets, so it remains finite. A and B are on both sets. So it's a partition that is contained, that contains both R and P. Right, it's the union of the two, so it contains the two. So by the previous proposition, that means the lower Darboux sum with respect to P is less than or equal to the lower Darboux sum with respect to R cup U, union P. A lower Darboux sum is always less than or equal to an upper Darboux sum on the same partition. And now a refinement, the upper Darboux sum can only get bigger. It can only get smaller. So note, what we've now actually proven is that for any two partitions, the lower Darboux sum with respect to P is always less than or equal to lower Darboux sum with respect to R. So that means for a partition P, this will always be a lower bound for the set of upper Darboux sums for any partition R, it doesn't matter. Which means this is always less than or equal to the infimum, which is our upper Darboux sum. And again, now we apply the same logic. P is arbitrary, so that means this is an upper bound for this set, which means that this is always less than or greater than or equal to the sup of that set, which was the lower Darboux integral. And there we go. Beautiful. So note, the main thing that we really had to prove was this little thing here, and that required the previous proposition. And like I said, it was a technical mess, but we needed it because it gets us this, and this is the money. This gets us everything that we need. This is why Riemann integration is going to work the way we expected it to work. All right. Okay, so before we go forward, we now know that the lower Darboux integral does not exceed the upper Darboux integral. Naturally, what we're probably going to do is define Riemann integration to be when those two things are equal. So before we do that, let's point out they are potentially unequal. So it's possible that you have strict inequality, and the classic example is this function, which you may remember as being something called the Dirichlet function. So on the interval 0, 1, we define the function as follows. For the rationals, it spits out 1, and for the irrationals, it spits out 0. Okay. Now, if you think about this function, you think about trying to stuff rectangles under it, you immediately go, oh boy, that's not really going to work very well, is it? And indeed, it doesn't. So for any partition, the infimum of the function on the K subinterval is always going to equal 0, because we can always find a rational number between any two real numbers, an irrational number, sorry, so it will spit out 0, and 0 is obviously a lower bound. And likewise, the supremum will always be equal to 1, because in between any of these we can find a rational, so it spits out 1 somewhere. So that means that the upper and the lower Darboux sums for any partition will always equal 0 because the infimums are actually minimums that are equal to 0. And likewise, the supremums are actually maximums. They're always equal to 1. And the summation of all of the delta sub k's is just the length of the interval, which is 1. So the lower Darboux integral is always 0, and the upper Darboux integral is always 1 for this horrible, horrible function. All right. Okay, so there we go. And hopefully you vaguely remember there are some functions that can't be Riemann integrated. And in some sense, they're sort of pathological nonsense. Like, why would you ever try to integrate this thing? Right. Well, if we really think about it, it does feel like this should have a Riemann integral, and it should be 0, right? Because even though 1 contributes, right, an infinite amount of times, the rationals versus the irrationals, well, there's way more irrationals than there are rationals, so it feels like it should, but note something about how the Riemann integration works. It cares about the partition. It doesn't care about the countability or uncountability of the sets involved here in the definition of the function. It just cares about the partitions, and the rationals and the irrationals are evenly distributed in the sense that they're both dense. So that kind of sinks the ship here. And going forward, we are only going to speak of Riemann integration, but some mathematicians disagreed with this and said, this is not good. I want this to integrate, and I want it to integrate to 0. So they came up with an improvement, with some quotes around that, of the Riemann integral called the Lebesgue integral. And if you're so interested, check that stuff out. Obviously, the name Riemann integral would, right, it's not the integral, it's the Riemann integral versus the derivative, right? So anyway, if you're interested, check that stuff out. But for us, we'll say a function is Riemann integrable if the upper and lower Darboux integrals are in fact equal. No more, no less. That's all it is. Okay, and so we're going to work with the set of all such Riemann integrable functions quite a bit. So the notation I'm going to use is as follows: R of AB. I'm going to use this R. Lebel, if I remember right, uses a fancier looking R. Oh, I deleted the wrong one. Oopsie doodle. Okay, yeah, so Lebel uses a fancier R for the set of Riemann integrable functions. He uses that one. Ooh, look at that. That's, ooh. I don't like that for the set of Riemann integral. I just like R. Math calligraphy R. Not just a plain R. A plain R I would consider what are called rational functions, so the functions that are a polynomial divided by a polynomial, but a fancier looking R would be for Riemann integral. Okay. All right, yeah, so there we go. So any function that's Riemann integrable, the set of all such things we'll denote as that. And if you're a Riemann integral, then these two things are equal to each other, so we'll just drop the bars to indicate them. Okay. The value of this, whatever this may be. And let's now make our first step towards creating an epsilon delta definition of the Riemann integral with a epsilon partition definition. So as we will, there's an extra R there now. All right, so as we will now demonstrate, a function is Riemann integrable if and only if given a epsilon, I can find a partition so that the upper Darboux sum minus the lower Darboux sum gets less than epsilon. Beautiful. All right, so there we go. This gives us our first pass at getting an epsilon delta, and so we're doing an epsilon partition. Cool. We will make epsilon delta soon. Okay. All right, let's do the proof of this, and the good news is we've effectively done the proof. So take something that's Riemann integral, take an epsilon. All right, well, the Riemann integral of this is the lower Darboux integral, which is an infimum. So given an epsilon, I can find an element out of my set so that it's strictly less than the infimum plus whatever positive thing I want. Right, this is the greatest lower bound, so if I make it any bigger, it's no longer a lower bound. There are things that it will now be bigger than, rather than less than. All right, and similarly, the Riemann integral is also the upper
Darboux integral, which means that if I make it smaller, I can find something bigger than it. All right, we're going to pull the same trick. We have an R, we have a T. So take the union, that's a partition, and now the upper excuse me. Okay, and that should be a yep. So the partition P, write the lower Darboux sum with respect to P must be less than or equal to the lower Darboux sum with respect to what happened? I think I no yeah P. The upper, yeah, blah, God, my brain is farting. Hold on, sorry. Yeah, right. So the upper, right. So with P, right, I added more to the partition R. Okay, I added the T, so the lower sum could have only gotten smaller. R was chosen. Yeah, the capital threw me off so bad. Sorry about that. The capital R was chosen so that this was less than epsilon plus 2. All right, but this is strictly less than epsilon, the lower Darboux sum of t plus epsilon, right? But t, if I now add the elements of r in, the lower sum only gets bigger, and epsilon over 2 plus epsilon over 2 gives me epsilon. And there we go, subtract that over, and we get the upper Darboux sum with respect to the partition P is minus the lower Darboux sum is less than epsilon. So we found our partition so that the upper Darboux sum minus the lower Darboux sum does not exceed epsilon. Okay. So there we go. Given an epsilon, you can find a partition. And note, we are once again invoking the refinement trick. Very powerful tool, and it will, again, will not be the last time we do it. And again, hopefully we remember to apply it appropriately, which I did, but right, the capital F, it got me. Because once I corrected it, I went back and I looked, and I was like, wait, is the P right then? Yeah, yeah. Anyway, Paul Rutz. Let's go. All right, so conversely, suppose that for every epsilon there is a partition so that the upper Darboux sum minus the lower Darboux sum is less than epsilon. I want to prove that my upper and lower integral are equal, so a way of doing that is proving that their difference in absolute value never exceeds any given epsilon. So, let epsilon be bigger than 0. I can find a partition. A partition. Oh my god. I don't think partition is not spelled correctly in both spots, and they're spelled wrong in different ways. Yeesh. 2 out of 10. Would not learn. Alright. Okay. Well, equipped with this, I now want to show that the upper and lower Darboux sums must behave. Okay, well, we know that the lower Darboux sum is always less than or equal to the lower integral. The lower integral, as we proved, is always less than or equal to the upper integral. And likewise, the upper integral is a infimum of all of the upper Darboux sums. So that means now, if I look at this difference, it is always greater than 0. This, by construction, is always less than that. This, its negative, is always less than or equal to this negative, and p was chosen to be less than epsilon. So we know this is greater than or equal to 0, but it's strictly less than every positive epsilon. So the only choice is that this must be equal to 0, and thus they are equal, and thus we are Riemann integrable. Beautiful. All right, so we've proven that if you're Riemann integrable, that can only happen if given epsilon, there is a partition so that the upper and lower Darboux sums are relatively close to each other with an epsilon. Beautiful. All right, well, now that's very nice. This is kind of missing a very nice feature. The traditional approach to the Riemann integral, of course, was Riemann sums, and that gave us a way of sort of computing things. While the upper and lower Darboux sums are theoretically nice, note that they're built off the backs of soups and imps, and hopefully, as we remember, actually finding soups and imps of things explicitly
is equivalent, right, to finding mins and maxes, which is a little bit time consuming. So, there is hopefully a better way of computing things, and indeed there is. Okay, here we're going to go a little bit for the remainder of these notes here. We're going to go a little bit off book. We're going to go a little bit different than how our textbook approaches Riemann integral stuff. Level kind of skimps on a couple of details, and he puts this as a homework problem, which I did not like. This is incredibly important. Okay, so given a bounded function on a non-degenerate interval, a collection of partitions is said to be Archimedean if you look at this difference and it goes to 0. And if you look at that and go, well, based on the previous proposition, this seems to indicate that the Riemann integral exists precisely when there's an Archimedean sequence of partitions. And note, a sequence. A lot better than given an epsilon there is some partition. Indeed. So, as we will now prove, you are Riemann integral precisely if you have access to an Archimedean sequence of partitions, and furthermore, if you can find such a sequence of partitions, it gives us a way of computing the value of the integral via a limit of a sequence. There we go. That's the good stuff. All right, and as we'll see, this gives us a way of explicitly computing Riemann sums. In fact, we will prove that the integral from 0 to 1 of x is equal to 1/2. I know. All right, but before we get there, we got to actually prove this. Let's do that. Okay, so suppose you are Riemann integral. Well, as we just demonstrated, for each n, we can find a partition so that the upper and lower Darboux sums of piece of n, that's what that's supposed to be, does not exceed 1 over n. So now just take the limit as n goes to infinity. And you've got an Archimedean sequence of partitions, because the limit of this goes to 0. All right. Conversely, suppose that there is an Archimedean sequence of partitions piece of n. Let epsilon be greater than 0. Since that limit is 0, at some point, this gets less than epsilon. And there we go. You must be Riemann integrable. Whee! All right, so not the most enlightening proof, right? Very easy and straightforward. But note, the power of this is that it now gives us a method for actual computation. Right, so that's really what the power of this lies. And note, it gives us a, given an epsilon, I can find a sequence, and working with that sequence gives me the computation I want. But now note, one last thing we need to prove, that the limit of the either lower or upper Darboux sum of the Archimedean partition actually gives us the Riemann integral. So note that this is true. Now, this means that if I look at the absolute value of the lower minus this, it doesn't exceed that. And if I look at the R, what the hell? Yeah, there you go. Right, so that means an absolute value, right, since this lives inside of the interval for this, if we look at these differences in absolute value, they don't exceed this, and each one of these goes to 0, which means each one of these will converge. And there we go. Actually, note, also, this is a monotone increasing sequence, so its limit is a supremum, and this is a monotone decreasing sequence, so its limit is a infimum. There you go. Look at that. Beautiful. It's a beauty. One in a million girls. Yeah. All right, cool. There we go. An actual method of computing Riemann integrals, and as promised, let us now use it to actually compute a Riemann integral. Specifically, we will formally prove that the integral from 0 to 1 of the function x is indeed 1/2. You know, you could just draw the triangle and easily compute that, but that's boring. Let's do some things. All right, so here's our first encounter with what's sometimes referred to as the uniform partition. So, given the interval 0, 1, I can partition it up in a, quote, uniform way by simply just looking at k over n. So note, example, if n was equal to 3, I would have 0, 1/3, 2/3, 3. If k was 5, I'd have 0, 1/5, 2/5, 3/5, 4/5, 1. So it cuts the domain up evenly into subintervals that all have length 1 over n. So this is sometimes referred to as the uniform partition or the equal partition, whatever you want to call it. All right, and now note, if I want to actually compute some upper and lower Darboux sums, it's super easy to do that. In this case, in fact, the infimum is the minimum, and the supremum is the maximum, right? Because if we're on this interval, the smallest thing is this. And if we're on this interval, the biggest thing is that. And the formulas are then here. So now if I want to compute, say, the lower Darboux sum, I know what all of the infimums are. Plug it in. I know what all the deltas are. Plug it in. Oh, look, ends, they get pulled out. And hey, a summation that we're hopefully very comfortable with, because I know that sums up to this. And, oh, look, one of the ends cancel, and I get n minus 1 over 2n. Oh, hey, look, when I take the limit, by the way, I get 1/2 here. Beautiful. All right, so we've got the lower Darboux sum for this sequence of partitions. Is that? We're now going to see that it must be Archimedean, because the upper ones sum up nicely as well, and the difference of the two gives me 1 over n, so I must have, that should be a piece of n there, so I have a Archimedean sequence of partitions, and thus I am integrable, and the value of my integral is the limit of the upper or the lower Darboux sums there, and that's equal to 1/2. So, yay! The Riemann integral is still intact after we've made it terribly rigorous. The integral of 0 to 1 of the function x, still 1/2. The area of a triangle with base 1 and height 1 is 1/2. The area of a right triangle did not, nothing weird happened because we made soups and imps. We just made the computation as tedious as possible. It's not that bad, though. All right, so there we go. Beautiful. All right. Okay, so we are almost there of getting our epsilon delta definition. So far, all of the stuff we've done with Riemann integrals has been built off the backs of upper and lower Darboux sums. We have not done anything with a Riemann sum, so let's talk about those. All right. So it's called a Riemann sum probably should say what it's for. Okay, so given a non-degenerate interval, a partition, and a partition, that right there is going to be called a Riemann sum for the bounded function f, again defined on a to b, real valued. I forgot the function word. Okay, so note, Riemann sum here, we are not adhering to a left-hand rule or a right-hand rule or a midpoint rule. A Riemann sum is simply pick a partition and then pick anything that lives in the subintervals and then just form the rectangles and add them up. Okay, so as we will now prove, and there is something to prove here. Oh, I'm missing the function of the hypothesis here again. Silly me. All right, so as we will now prove, if we look at the collection of all possible Riemann sums, this collection is bounded below, and the infimum of those is the lower Darboux sum, and the supremum is the upper Darboux sum. So note, every Riemann sum is going to live somewhere between the lower and upper Darboux sums, and since we know we can make these things converge to the integral, that means we can make these things converge to them as well. Hooray! Okay, cool. All right, so note, there is a bit to be done here, right? We're not just immediately, this is not as immediate as you think it would be, right? Because note, we're proving this is a infimum. It should be obvious this is a lower bound, and that this is an upper bound. But the fact that they're the inf and the sup, that requires a bit of work. And check out my fancy R. All right, so let's prove it. So the supremum of all Riemann sums is the upper Darboux sum, and the infimum of all Riemann sums is the lower Darboux sum. Okay. Yeah, you know the deal. Okay, so first things first.
the lower Darboux sums are always less than or equal to whatever Riemann sum you can create, right? Because the m of pkf that we make is the infimum, so if you choose any element, the infimum is smaller than it. So there we go. These are always strictly positive real numbers, so you can multiply them across the inequality without screwing anything up. So this is indeed a lower bound for the collection of all Riemann sums. That does not mean it's the infimum. So let's prove it has to be the infimum. So the infimum note would be less than or equal to, would be greater than or equal to any Darboux sum. Would be the Darboux sum with respect to the partition P. So let's suppose that it's strict. Okay. So let epsilon be the difference of that. Note that epsilon is positive. Now, on all of those subintervals, we have an infimum. And if I add something positive to it, there's got to be something. I can choose something that it got bigger than. Right, this is an infimum, so if I add something to it, there's something from the set less than, because it's no longer a lower bound. All right, so I can find a choice of elements in my subintervals and note that this is a Riemann sum, and so it's greater than alpha. Each one of these, though, is strictly less than that, and these are strictly positive, so when I multiply them across, the strict does not go away. All right, and then now if I do these sums, well, here I'll just pick up the summation of LP, of the lower Darboux sum of PF on the partition P, and if I add all of these up, oh hey, that will cancel that, and we'll just get epsilon, but that is what alpha was chosen, so we now have a beautiful contradiction. In fact, our favorite one, a real number being strictly less than itself. Okay, so that means that the infimum of the collection of all Riemann sums must in fact equal the lower Darboux sum. Beautiful. Cool, cool. So, no, like I said, there is a little bit of work to be done, because the obvious thing is that this is a lower bound for that set. The non-obvious thing is that it's actually the infimum, and that required us to be a little clever. And note, we kind of snuck in b minus a. I wonder if we're going to pull that trick off, and I don't know, we're proving continuous functions are integrable. All right, beautiful. Okay, so we've got one more thing to discuss, and before we get to our epsilon definition, or epsilon delta definition of the Riemann integral, and that is the mesh of a partition, which we've already noted. So in the very first slide, we had this symbol show up, and for a partition, that is just simply the maximum of all of the lengths of the subintervals. Note it's a finite collection of positive things, so this has to be positive. All right, and here we go. Our epsilon delta definition of the Riemann integral. So compare, remember, you should have made a guess as to what this should be, and here it is. So if I have a non-degenerate interval, I have a bounded function, and I have a real number with the property that given an epsilon greater than 0, there exists a delta, so that any partition whose mesh, the thing that we're limiting, is less than delta, the Riemann sums are always within epsilon for any partition whose mesh, whose maximum subinterval length does not exceed delta. Okay, if you have a bounded function and a real number with these properties, given an epsilon, there is a delta, so that any partition, so that the maximum subinterval size does not exceed delta, then the number I is always within epsilon of any Riemann sum, does not matter if it's left or right, hand pointed rule. Then you must be integrable, and the I you have is indeed the integral. All right, so there it is. Here is a function is Riemann integrable, and its integral is equal to this number I. If given an epsilon, I can find a delta, so that all partitions whose meshes is less than delta, the Riemann sums are always less than epsilon. So given an epsilon, there is a delta definition for the Riemann integral. Beautiful. All right, so let's prove it. All right, we're almost done. Note, I didn't write this as an if and only if. Keep that. Put that in your that comment in your stupid pocket and think about it. All right.
Okay, so let's prove that if things work, then things work. So in other words, give it an epsilon, there is a delta, so that things behave. All right, well, 1 over 2 to the n is a positive epsilon, so I can always find a delta sub n greater than 0, so that any partition whose mesh size does not exceed delta sub n, then any of the Riemann sums that you can cook up get within 1 over 2n of I. Right, so our hypothesis guarantees that. Given any epsilon, there are deltas, so that things work the way I want them to. All right, now for each n then, since delta is positive and so is b minus a, I can find a natural number 1 over capital M sub n that gets strictly less than it. All right, and then let's create the uniform partition going from 0 to m sub n on the interval AB. Now note here it's a little bit more involved than on an interval 0 to 1, or indeed on any interval that starts with 0, because you're just adding 0, so you don't need to care about it in the notation. All right, so by construction, this thing right here, the sub-interval lengths are uniform, they're always the same, and oh, looky here, I made sure I picked them so that A, they were less than delta over n. So that implies then that I, our number here, gets within 1 over 2 to the n of any of these Riemann sums. Beautiful. All right, so I now have specific sums where things are behaving nicely. So now what do I do? All right, well, I need to prove that I'm Riemann integrable, which means that I needed to, I don't know, create some partitions so that the upper and lower Darboux sums get within epsilon. All right. So, for our partition P sub n that we created, by picking uniformly some points, we can look at the collection of all possible Riemann sums. And as we just proved, the infimum of that is the lower Darboux sum, and the supremum of that is the upper Darboux sum. That means that if I look at all possible Riemann sums with respect to the partition P sub n, note if I minus I from that, that cannot get any smaller than negative 1 over 2 to the n. So in other words, I minus 1 over 2 to the n is a lower bound for the set of all possible Riemann summations of the function f on the interval P on the partition P sub n. Since that is a lower bound and this is the greatest lower bound, we must have this inequality. And likewise, we can do the same thing with the upper Darboux sum and get that that is less than or equal to 1 over 2n plus I, which then means that, oh, bada bing, bada boom, I've got an Archimedean partition. All right, so I have an Archimedean partition, which means that we must be Riemann integrable, and our Riemann integral is equal to the limit of those. And note by construction, the limit of the upper sums is bounded above by I, because again, these are always less than or equal to that. And likewise, the limit of the lower Darboux sum is greater than or equal to I. So they actually must equal each other, and there we go. We're Riemann integrable. And the I, given an epsilon, the thing that we can get the Riemann sums within epsilon for any delta, must actually equal the Riemann integral. Beautiful, there we go. So, given an epsilon, if you can find a delta so that any partition whose mesh size, largest subinterval, does not exceed delta, then all of the associated Riemann sums you can make for any of those partitions is within epsilon of I, then our function is integrable, and I is equal to the integral. So there we go. We have now officially proven Riemann integrability in an epsilon delta way using Riemann sums. Just like calculus. Only now, in epsilons. All right, now you might be going, well, all right, it seems like we're close to wrapping it up here, but I still see some slides. Yeah, so note, back here, I pointed something out. This gives me epsilon delta conditions to ensure that I'm integrable and that my Riemann integral lines up with my Riemann sums. What about the converse? Right, what if I am Riemann integrable? Then does that mean for any epsilon there has to be a delta? Right, so we've proven that if for every epsilon there's a delta, things work. you're Riemann integrable. What about the converse? If you're Riemann integrable, then given an epsilon, can you find delta so that this happens? Right? No, we didn't prove that here. We proved one direction. And it turns out it is true. So, indeed, if you are Riemann integrable, then given any epsilon, then there is a delta so that any partition whose mesh size does not exceed delta, then the Riemann sum gets within epsilon of the Riemann integral. This is in fact true. However, I split it because, as you're going to see, the proof of this is shocking. This seems like this should be pretty easy to prove, but it is kind of not. It involves an incredible trick that is not at all obvious whatsoever. So the previous one, hopefully you kind of followed it, and it all was sort of like, okay, that makes sense, and okay, that makes sense, and okay, that makes sense. A lot of just sort of, yeah, I see this stuff all working. Here, this is going to be a very classical analysis proof in the sense that a bunch of shit is going to happen in the beginning, and it's not going to make any goddamn sense until you get to the end, where it makes perfect sense. So, that being said, since we are integral, that means we can find a partition R with capital N things, keep track of that, so that the upper Darboux sum minus the lower Darboux sum does not exceed epsilon over 2. Okay, so first off, nothing too crazy, right? We've proven Riemann integrability means that I can find partitions so that I can do this, and okay, an epsilon over 2, sure, that happens. Alright, well, f is bounded, right, because f is Riemann integrable, which, and again, we only define Riemann integrability for bounded functions, so, alright, there's a positive b, so that f is less than or equal to, okay, alright, not too crazy showing up here. Alright, now for the crazy. Alright, let delta equal this. Epsilon over 4 times b times n plus 1. Sure, why not? Why? Obviously you picked this. Alright, and going into it, maybe it might be a little like, yeah, okay, sure. Now, no, what we need to prove, we need to prove that if you have a partition whose subintervals don't exceed the length of this, then any of the Riemann sums on those partitions get within epsilon of the Riemann integral. And sort of initially, this is, how does this work? It's not clear at all how this works. Well, buckle up, I'll tell you why. So, take any partition whose mesh size does not exceed delta. Okay. Now, there are two things to do. So obviously we're going to use R as kind of a pivot point, but we're not immediately going to just go to the union of these two, like as we've done before, where we're like, oh, just glue these two together, and then lower and upper Darboux sums have to behave. It turns out we gotta be a little bit more clever about how we approach this. So we're going to use this as a pivot. So what we need to do is look at how do these elements in this list compare to this one. Okay, so I claim that UP of F and LP of F, so again the upper Darboux sum of P and the lower Darboux sum, they don't exceed epsilon, and then that's going to be what we need. So the trick, it turns out, is to do the following. Look at all of the indices K, so that my subintervals, note K is, X is for the partition P whose mesh size is less than delta, and the Y's are the initial partitions so that the upper and lower Darboux sums difference does not exceed epsilon over 2. Okay, so look at all of the indices so that the subintervals don't include anything out of Y. And note that there would have to be some of these, potentially, or they're just, all the same. So what we're doing here is basically going, all right, look at the subintervals that, for the partition P, that have nothing to do with the subintervals, the initial subintervals for the partition R. Okay, so note that for any K then that lives in A, there has to be a unique element J, so that Y sub J minus 1 and Y sub J are greater than this subinterval, right? Because Y sub J is, none of these are in there. So at some point, while these are being listed out, they have to hop over that subinterval. Note, that would mean then that the size of the subinterval is strictly less than the size of this subinterval, and then the upper and lower, then the infimums and the supremums behave accordingly. So that means that if I were to look at this summation, so the difference of these things times the size of the subintervals, all right, every k that lives in here out of A, well, there is a j that it's less than. So if I were to add up all of the j's, that would be bigger than this. And note, by construction, this is the upper and lower Darboux sum of f, the difference of those two, less than epsilon. Right. Note I combined it into one term. Hence, if you're like, whoa, why are we doing that? It's like, well, it's because we want to look at this difference right here. All right, so for all of the indices k running from 0 to n, so that y sub j misses it, right, all of these, right, this is just, these terms are just going to be less than or equal to some terms that show up here. So there you go. This part needs to be less than epsilon over 2. So now let's look at the set B, which consists of all of the things in the list 0 to n that are not in A, which means that if you are in B, there is some y sub j that must live in the subinterval there. So note, this forces B to have at most n plus 1 elements. Oh, good thing I have that n plus 1 on my delta. Right, now why would that be true, right? For everything that lives in K, there is some J that lands in here. So every K has a Y sub J that it corresponds to. Right, so B cannot exceed the number of elements that came out of the partition R, of which there are n plus 1. Right, because for each K, there is one of them that it corresponds to. So B can't have more than that. Right, otherwise, right, then you've got more things in Y than you have in your list. Okay. All right. Oh, shit, I shouldn't have used B, because that's my bound. Oh, I'm an idiot. All right, let's call it set. Oh, my God. How did I not notice that when I was typing? Oh, my, oof. Oof, oof, oof. Oh, let me fix that. That's gonna be horribly confusing. Oh god. All right. Anyway, all right. So yeah, our set C, which is equal to that. Now B is our bound for our function, and now note f lives between negative b and b. So if you look at the supremum minus the infimum, well, it doesn't get any bigger than twice b. Okay, and now we finally use the fact that the partition mesh size was less than delta, right, this then here cannot exceed delta. All right, and then so if we add up all of the terms whose index lives in the set C, if we add up all of these terms, well, okay, each one of these does not exceed 2b times delta, and there are at most n plus 1 of them. And there we go, we chose delta so that this would be equal to epsilon over 2. So that means that if we look at the lower, get that C in, if we look at the upper Darboux sum minus the lower Darboux sum, it's this summation. And as we pointed out, if K is hanging out, that should be a 1, yeah. Catching all these little minor mistakes there. Yep. Right, so, right, that means if we look at all of these sums here, right, if you're in the set A, then we know this whole sum needs to be less than epsilon over 2, and likewise, if you land in the set C, this all needs to be less than or equal to epsilon over 2. Those add up when we get epsilon, all right? And there we go. We've now proven that any partition whose mesh size gets less than delta, the difference between their upper and lower Darboux sum does not exceed epsilon. So now let's finish it off. That means if we form a Riemann sum, since we picked any element, it's bigger than the infimum and the supremum. F of x sub c lives in there. Okay, and that means that the lower Darboux sum and the upper Darboux sum trap the Riemann integral. Similarly, the integral is trapped between the two, so if you look at the difference of these two in absolute value, it cannot exceed the difference here, which is less than epsilon, and there we go. We have now proven that if you are indeed Riemann integrable, then given any epsilon, any partition whose mesh size does not exceed delta, the Riemann sum gets within epsilon of the Riemann integral, and oof. There we go. We are done. We did it. We have proven that the Riemann integral, as seen in Calc 1, a limit of Riemann summations as you let the mesh size go to 0, that is indeed still true, and there's an epsilon delta argument for it. Beautiful. All right. All right, so we've now got the Riemann integral on firm, rigorous grounding, so now it's time to start proving things about it. That's what we'll do next time.